Okay, am I audible to you?
Yes, sir. Audible, sir.
Screen is visible?
Yes, sir. Visible, sir.
Right? Okay, right. So we'll start the class. So yesterday's class we discussed about helical gears and we have seen how we can convert an helical gear into an equivalent spur gear. We'll call it as a virtual spur gear or formative spur gear. So now we'll see. We already discussed what are the parameters we need to consider to calculate the beam strength of spur gear. So now, if you are able to convert the parameters of helical gear, those parameters into equivalent virtual gear, spur gear, then you can find out what is the beam strength for a helical gear also. Similarly, not only beam strength, you can calculate the wear strength also. So now we'll see what are the expressions for beam strength as well as wear strength for a helical gear or helical gear drive. So in order to determine the beam strength, the helical gear is to be considered to be equivalent formative spur gear. That's what we already discussed. The formative gear is an imaginary spur gear or virtual spur gear in a plane perpendicular to the tooth element. This is the important point. So here we are converting that helical gear into an imaginary spur gear or virtual spur gear in a plane perpendicular to the tooth element. Only in that direction only it is equal to the spur gear. If you go for plane perpendicular to the plane parallel to the tooth element or plane of rotation, not the plane of rotation, then it is not going to be the ever equivalent spur gear. So here we are considering this imaginary spur gear in the plane perpendicular to the tooth element, or you can say plane of rotation. The pitch circle diameter of the gear is D dash and the number of teeth is Z dash and module is Mn. So now for this virtual spur gear, actually the pitch circle diameter will denote it as D for helical gear, but D dash. So actually while calculating this beam strength, you need to consider it as D dash and number of teeth is Z dash, not Z. It is again virtual number of teeth. So we know the relation between virtual number of teeth and actual number of teeth, and also we know the this D dash is nothing but the pitch circle diameter of your virtual spur gear, and there is a relation between this D dash and D, where D is the pitch circle diameter of the helical gear, and then Mn should be the normal module. So the module should be, you need to consider is in the beam strength for the helical gear, you need to consider as Mn. So now, if you are know these are the only parameters we need to consider. If you take spur gear equation, okay, anyway, I'll show that in that your beam strength of spur gear consists of SB is nothing but it is equal to M B sigma Y or sigma B, bending stress, allowable bending stress sigma B into capital Y. So this is the equation what we are taken. So here also the equation remains same. Only thing is these parameters, whatever parameters you have, M, B, sigma B and Y, those parameters you need to consider only for the equivalent spur gear. So in case of equivalent spur gear, your M is nothing but Mn. So that means the M will be replaced by Mn and phase width B will be replaced by B cos phi, and sigma B itself, that is the allowable bending stress in the material, no need to change that, and this Y, that is Lewis form factor, this is calculated based on this virtual number of teeth, not the actual number of teeth. So with this, that you can easily derive an expression for just by substituting the equivalent parameters of that virtual spur gear in the equation for beam strength of the spur gear, you will get the equation for beam strength of a helical gear. So only thing is what you need to do is you need to substitute equivalent parameters of those virtual gears. So now, like I said, the beam strength of spur gear is given by, this is the formula, SB is equal to M into B into sigma B into Y. M is module there, B is phase width, and sigma B is the allowable bending stress, and Y is Lewis form factor calculated based on the number of teeth. Now, if I want to use this formula for the helical gear, then what are the modifications I need to do this formula? So that will illustrate, this figure will illustrate that. So here, this is the plane of the rotation. So this is the force which is acting in the plane of rotation. So your format spur gear or virtual spur gear is, we'll consider that one as the helical gear, we'll consider it as a virtual spur gear in the plane of rotation or in a plane perpendicular to the tooth element. So this is the tooth element. So this is perpendicular to this. So therefore, you need to consider these parameters to convert this beam strength equation of spur gear into an equivalent helical gear. So for that, so okay, that's what he said. This equation is also applicable to the formative spur gear. So whatever beam strength equation is there for your spur gear, that is applicable for even your formative spur gear. Only thing is, in this equation you need to substitute what are the parameters of this formative spur gear. That means what is the module, what is the face width, what is the allowable bending stress, and what is the Lewis form factor for this formative spur gear. You will get the beam strength of helical gear also. So, but what are those parameters? We'll see one by one. So now, like I said, if you refer to this figure, your SB. So here this is SB, and the resultant force will act always through the pitch line, something like this, and the angle is here this psi, which is nothing but your helix angle. So this be SB of N. So now the force which is acting here, this in this case, this SB is the force acting along the pitch line. So here the force acting along the pitch line is nothing but this one. But if I want to write an expression for beam strength, so I can find a relation between this SB and SBN. So that is, our SB is nothing but SB of N into cos psi. So that is one relation you need to substitute. That means, so as in place of SB, you have to substitute as SB of N cos phi. Or if I want to use SB itself, so I can modify that accordingly. So I need to take this equation. If this equation is divided by cos psi, I'll get this equation for the helical gear. That is one parameter. Then if we substitute that SB is equal to M, so in place of M, I need to substitute NM, and in place of B, what I said is you need to substitute B by cos phi, and then in place of sigma B, it is sigma B only, and Y will be taken as Lewis form factor calculated based on the virtual number of teeth. So only modification you are doing here it is, you are replacing the module M by Mn, that is normal module, and this your Lewis form factor is calculated based on virtual number of teeth, not on based on the actual number of teeth on the helical gear. So that is the only thing. So therefore, this is the equation which you can call it as Lewis equation for helical gear, beam strength of a helical gear. So this equation, the form factor Y is based on the virtual number of teeth. So like I mentioned, equation gives the beam strength in the plane of rotation. So this is the important point. So this is gives the equation in the plane of the rotation. So this is the beam strength in the plane of rotation, not along the pitch length or pitch line. Therefore, the beam strength indicates a maximum value of tangential force that the tooth can transmit without bending failure. So now if you want to define beam strength, so of course this definition is same for helical gear as well as spur gear. You can use the same definition. So beam strength is nothing but the maximum value of tangential force, that is PT, P suffix T, that the tooth can transmit without bending failure. That we'll call it as the beam strength. So now you have a similar equation, even for helical gear also you have a similar equation for the beam strength. Only thing is your module M, you see here this is the equation for the spur gear, and here this is the equation for helical gear. So this is for spur gear and this is for helical gear. Now if you compare these two, the only modification here is this M will be replaced by Mn, and this Y should be here, this Y should be calculated based on virtual number of teeth. So that is the only thing you need to do that. So otherwise they are same only. Okay, so this is how it should be, always more than effective force between them. Okay, so here the bending strength, in order to avoid failure, the beam strength should be always more than the effective force between the meshing teeth. Then the teeth is going to be safe or teeth is not going to fail under bending. So in order to avoid bending failure, this bending strength should be more than the effective force between the meshing tooth. Okay, so this is about the beam strength of helical gear. Similarly, we try to calculate what is the effective load on the gear tooth, and then, like I said, for design criteria, your SB beam strength should be greater than effective load, P effective. So again, here also there are two ways calculation of this effective load. That's what we have seen in case of spur gears. Those are, if you use velocity factor, then that is one approach, velocity factor. The other approach is you need to use Buckingham's equation to calculate the dynamic load PD. So now we'll see what are the formulas for these two. So if I want to use velocity approach, so what is the velocity factor I need to consider? If I want to use Buckingham's equation, what is the expression for PD? Then once you have this dynamic force, from that you can easily calculate the effective force. In order to determine the beam strength, the helical gear is considered to be equivalent spur gear. The formative gear is okay. Again, it is, I think it is repeating. Okay, maybe a repetition of the slide here. This one. Okay. Okay. So now here, in order to calculate the effective load, so your formula for P effective is CS into PT. Then if you want to use Buckingham's equation, it is going to be PD. So this is the formula for your P effective. Or if you want to use velocity factor approach, it is CS into PT. Then if you use data book, the formula is here, it should be multiplied by CV. Okay, so these are the formulas. So now in this both the formulas, I need to calculate PT. So now I will get the PT, I will get that PT, that is transverse force or tangential component of the force on the gear tooth from the torque transmitted. So we know expression for MT. So this is the expression for the torque transmitted. Then you have a relation between MT and PT, that is the transverse force through pitch circle diameter. D dash is the pitch circle diameter. So here this D dash is nothing but the pitch circle diameter of your virtual spur gear, not actual pitch circle diameter of the helical gear. You have to use virtual pitch circle diameter of your virtual spur gear. So therefore PT is nothing but 2MT by D dash. So I got PT value. Then the value of tangential component therefore depends upon the rated power and rated speed. So here this value, this tangential component of the force will depends upon rated power and rated speed. So this M depends upon power and N. So therefore your PT will also depends upon M and this rated speed as well as rated power. The above value of tangential component therefore depends upon the rated power and rated speed. In addition to that, there is a dynamic load. So in addition to that, dynamic load is there. Like I said, so the dynamic load you can estimate by two methods. One is the approximate estimation by means of velocity factor in the preliminary stages of the gear design, and precise calculation by Buckingham's equation in the final stages. So here you can use any one of these two methods. Either you can go for velocity by applying the velocity factor, that is going to be approximate method, or if you want to have a precise calculation, you need to use Buckingham's equation. So now what is the velocity factor we need to consider, and also of course the CS is nothing but the maximum torque by the mean torque, which can be expressed as PT max. So once you have a CS, your PT max is nothing but CS into PT. Then coming to the dynamic load, now if you want to use the velocity factor approach, so then the velocity factor is given by CV is equal to 5.6 by 5.6 plus root V. So you have, in case of spur gear, you have three relations, whereas in case of helical gear, you have only one relation. So only you have to use this relation. Of course, in our data book, he has given it is 5.6 plus root V divided by 5.6. So you can take, if you want, you can take in that way. So in that case, I'll take it as 1 by CV. So this 1 by CV is given as something like this. So therefore, This is the velocity factor. If you multiply this velocity factor with respect to CS into PT, you will get the equivalent load. So in this case, your V is nothing but pi d dash n by 60 into 10 cubes. So here this d dash is nothing but again the pitch circle diameter of the virtual spur gear. So you need to remember that point, or you need to make a note of that. So we are not using the pitch circle diameter of the helical gear. We are using pitch circle diameter of the virtual spur gear. So that is the important point. So the effective load between the two meshing teeth is now it is, since if I am taking CS is equal to 5.6 by 5.6 plus root V. So inverse what he has given, inverse of what he has given in the data book. So therefore your P effective is CS into PT by CV. So here it is 1 by CV. So I'll get like this. So this is how we can calculate the effective load using velocity factor approach. Now if I want to use Buckingham's equation, so if I want to have a precise load or precise dynamic load, we need to go for the Buckingham's equation. So in that we should know what are the errors. So again here in the textbook he specified the errors in the grades, but in the data book we have only three groups of error, whether it is a commercial gears or carefully cut and precisely cut gears. So we have a table of that. We'll use the table to solve this problems related to this one. So then if you want to use Buckingham equation, this is going to be the equation for your effective force. So P effective is equal to CS into PT plus PD. So now once I have a P effective, I can calculate, or I can decide, or I can design whether the gear is going to fail for the given load or not. So accordingly you can design it. So okay, now if you want to see the formula for dynamic load due to this Buckingham or from the Buckingham equation, so this is the formula. So there is a slight variation here. You have a additional term here cos square psi. Here also you have cos square psi. Earlier you have 21 into B CEB. So earlier you don't have this helix angle. So because of helix angle, this comes into picture. Even you have a cos psi here. Okay. Anyway, no need to remember this. This is given in our data book or the material what I already shared to you through WhatsApp. So in the document, these formulas are there. So straight away you can use those formulas. So no need to remember all these things. Okay. PD is the dynamic load. V is the pitch line velocity. C is the deformation factor. If I take it is C into E, C I'll call it as deformation factor. But in our data book, he has taken CE as a only single C. So he has called it as dynamic factor. So whatever you call it as, and the unit for this one is Newton per mm. The unit for C what he has given in the data book is Newton per mm. But here in this formula, if you take C into E, it is going to be Newton per mm square. Okay, error is again this error value, E value is taken from the data book only. That is nothing but sum of error between the two meshing teeth. Face width, tangential force due to rated torque. Then in order to avoid a failure of gear tooth due to bending, your SB should be P effective, greater than P effective. So your beam strength should be greater than P effective. So that you need to consider. Okay, introduction. Okay, now if you want to use factor of safety into design, this equal symbol, greater than symbol can be replaced by equal sign. Therefore, your SB is equal to P effective into factor of safety. This is what we done in case of spur gears also. The same thing. Only thing is a little bit modification to the formulas for dynamic load as well as effective load. So that you need to do it. Then coming to the wear strength equation of spur gear, again we'll take the same thing. So for this purpose, a pair of helical gear is considered to be equivalent to the format pinero and format gear in a plane perpendicular to the tooth element. The same thing. The wear strength of the spur gear is given by, this is the equation for the wear strength of the spur gear. SW is equal to B, Q, dp dash and K. So in that again what you have to do is you need to convert these parameters. If you want to convert this one into an equivalent helical gear or equivalent virtual spur gear, equivalent to the helical gear of which is nothing but a virtual spur gear. So then you need to substitute what are their corresponding parameters here. Q is going to be remain same. It is not going to change because you have a ratio above and your Q factor, that is ratio factor is nothing but Z into Z divided by 2 into Z into Z by ZZ plus ZP. So this is the formula what we taken for Q. Whether you use virtual number of teeth or actual number of teeth, it doesn't matter. It is not going to change. It is going to be same only. So therefore, either you can use same formula what you are using for the spur gear, or you can use this virtual number of teeth. It doesn't matter. Then DP is just now we have seen how we can calculate the pitch circle diameter of your virtual spur gear. So the formula for this one is dP by cos square psi, where this dP is the pitch circle diameter of the helical gear, which is nothing but mn module, normal module into number of teeth z. So you can calculate dP dash, and B is B by cos psi. So face width along the tooth element, because here we are considering this one as a spur gear which is in the plane perpendicular to the tooth element. You need to convert. Similarly, so I think here this SB can be replaced by SW here, the same equation. So then there is a relation between SW and SWN. So where is SW is equal to wear strength perpendicular to the tooth element. The relation between here two things are there, only one here. So SW is nothing but SW of n into cos psi. So from this triangle you can easily find that. So now if you substitute all those parameters into this equation, you will get your SW is equal to B D Q dP K divided by cos square psi. So this is going to be the equation for your wave strength equation. Wave strength equation for a helical gear. Again, you compare K remains K, B remains B, Q remains Q, and dP here pitch circle diameter dP. So it remains same. It is so it's similar to the previous problem, but only thing here is you have a additional term cos square psi in the equation. Or else, if you want to convert or if you want to replace this dP by dP dash, so maybe some books he has given like that also. dP can be replaced by dP dash. So in that case, this dP by cos square psi can simply replace it as dP dash. So that's it. So what you are going to get? B into Q into dP dash K. Simple, same as the previous formula. So here you can see it is same as the previous formula, but only thing is now here this dP dash is nothing but the pitch circle diameter of your formative spur gear or formative pinion. Here it is always in case of this helical gears, it is based on the design is based on the pinion. So you have to take the pitch circle diameter of formative pinion. So if the formula remains same, if you replace this dP by dP dash, it remains same. Only thing is you need to use the pitch circle diameter of the formative spur pinion. That is the only thing you need to do it, right? So this is how you can calculate the beam strength of wear strength of helical gear also. So once you have equations for beam strength and wear strength, now you are in a position to design the gear. So like I said, the procedure is similar to the spur gears what we have discussed. So now we'll take up some numerical problems on this also. So okay, so this equation SW, that is nothing but BQ dPk by cos square phi, is known as Buckingham equation for wear. Equation gives the wear strength in the plane of rotation. Therefore, wear strength indicates the maximum tangential force that the tooth can transmit without fitting failure. So due to wear, there is a failure. We'll call that failure as a fitting failure. So fitting action will be there. So because of that, the gear is going to worn out and it is going to fail. So therefore, to avoid that fitting failure, the wear strength should be more than your effective force, P effective. So that is the condition you need to use. In order to avoid failure of gear tooth due to fitting, your wear strength should be greater than effective force. If you want to introduce the factor of safety, then your wear strength is nothing but P effective into Fs. So this is how you can design the gears, helical gears, either based on beam strength or wear strength. Okay, right. So now once you understand these things, now we can move to the numerical examples. So in that, this is the first problem what we are going to consider. Just you note down, so then we'll discuss the solution for this also. So take a 1 or 2 minutes time to note it down, then we'll discuss the solution. Okay, is it over? Is anybody there in the class? Two members are there, but nobody is responding.
Sir, 1 minute, sir. Note చేసుకుంటున్నాను సార్.
నోట్ చెయ్యి త్వరగా చెయ్యి. ఎంత టైం కావాలి? 4 దే ఆర్ 6 lines or 7 lines. So how much time it take to note down 7 lines?
సార్ కంప్లీట్ నోట్ చేసుకున్నాను.
Okay, so we'll see the solution for this now. First I'll read the problem data, then we'll see the solution. A pair of parallel helical gear consists of 20 teeth pinion meshing with a 100 teeth gear. So the meaning of this parallel helical gear means the axis of the two shafts which connects these helical gears are parallel. So that is the meaning of that. So the two shafts axes are parallel to each other. So then these two helical gears are called parallel helical gears. It consists of 23th pinion. So let us say if I take this is pinion and this is the gear. So on pinion number of teeth your ZP is 20. See here these 20 are the actual number of teeth, not the virtual number of teeth. So we need to calculate the virtual number of teeth to design the gears. So ZP is 20 and ZG is 720. So that means he has given the speed ratio. I is also, your I is nothing but omega P by omega Z, which is nothing but ZG by ZP. So now, you know, if you know the speed of the pinion, you can calculate speed of the gear or based on this relation. So he has given the number of teeth on pinion and number of teeth on gear, you can calculate that. Of course, he has already given the pinion speed also. Pinion speed is 720 RPM. The normal pressure angle is 20 degrees. So normal pressure angle we denote it as alpha n. We'll use only alpha n in the equations. So alpha n is given as 20 degrees. Helix angle is 25 degrees. Psi is 25 degrees. Then the face width B is 40 mm. Face width is 40 mm. And the normal module is 4 mm. So normal module we denote by Mn, which is 4 mm. Then pinion as well as gear is made of steel 40C8. So that means both pinion and gear are made of same material, in the sense obviously the pinion is going to be the weaker one and the design should be based on the pinion. So for that he has given SUT is 600 Newton per mm square. Then if SUT is given, your sigma B, that is allowable bending stress, is nothing but SU2 by 3, which is nothing but 200 MPa or 200 Newton per mm square. That is also given. Then the heat treated, okay, and heat treated to the surface hardness of 300 BHN. So the surface hardness of the gear tooth also given BHN as 300. The service factor and factor of safety are 1.5 and 2. So service factor is CS, which is given as 1.5, and factor of safety FS is 2. Then assume that velocity factor accounts for the dynamic load. So that means he asked us use the velocity factor approach. That means you need to calculate CV. So based on this CV, you need to calculate the effective load, and based on that, you have to calculate what is the power transmitting capacity of this gear. So first you need to calculate PT. So once you have a PT, so then using this you can calculate MT. Once you have MT, from the MT you can calculate the rated power P. So this is quite similar to the previous problem what you discussed or what we solved in case of spur gear. So but only thing here is, so once you write in the data, you need to use the formulas corresponding to the virtual spur gear, and you can solve this particular problem very easily. Okay, right. So speed of the pinion, number of teeth on pinion, number of teeth on gear, module, normal module, and normal pressure angle, helix angle, face width, SUT, BHN, CS, and FS. So this is the given data. Then, since both the gears are made of same material, pinion is the weaker than the gear, so design should be based on the pinion. So now you have to calculate what are the virtual number of teeth on the pinion. So the formula for that virtual number of teeth is, okay. If you have any doubt, so how we got this formula? So these formulas are there in our data book or the material what I shared through WhatsApp. In that also he has given these things. So if you refer that, in that he has given the second page what I shared in that. So in that he has given the formulas for the helical gears. So you can see that, or else if you have a data book, even in the data book also he has given those formulas. But only thing is we use the psi here for the helix angle, but he has used the beta for the helix angle. That is the only thing. So YV Lewis form factor. So if you refer that one, 28 point H22 the formula, or H11. If you take helical gears is there in the under the heading, he has given Lewis equations. Beam strength of helical gear F suffix B is equal to sigma B into B into phi into Mn into YV. The same formula what we have taken, only YV is what he has given. YV is nothing but the Lewis form factor, which depends upon the virtual number of teeth. ZB is equal to Z by cos cube beta. So here we have taken ZB by cos cube psi. Same thing. If psi is the helix angle, he has used the beta as the helix angle. Then he has given the design tooth load FD is equal to P into KS into CV by V. The same thing you can use for this also, CS and CV. So if you see that the formula for CS directly they will give it the that is maximum torque per rated torque. You need to calculate it if not given in the problem data. Then KS is the service factor he has taken. We have taken it as service CS. Then CV formula we know that you have to use that CV formula. Then for safe working, your FB should be greater than FD. So that's what he has given. Similarly, Buckingham equation is also given. Dynamic load acting on the helical gear tooth FD is equal to same thing what I have given in the book. So that is nothing but your FD is in fact it's not FD formula, it is a equivalent load. So you can say it dynamic load, total dynamic load he has given. Formula for total dynamic load, that is P effective he has given. What we are calling it as P effective. So that formula is given. Similarly, wear strength formula also given. Wear strength FW is equal to D1 into B into Q into KW by cos square beta. So whatever formulas just now we discussed, those formulas are given in the data book. So now here this formula is there in your data book. So you can use that one. That is nothing but your equation 28.H21. So from that you will get your virtual number of teeth. So now based on this virtual number of teeth, now you need to calculate your Lewis form factor to calculate the beam strength. The Lewis form factor is obtained by the interpolation using data from the table 28.233. So whatever data I shared it to you in that information, the table number 28.33, you need to use it for calculating this Lewis form factor. See, in that you don't have fractional numbers. So whatever table we consider there, you have a 26 teeth are there. After 26, you have 28. So Lewis form factor is available for 26 teeth or 28 teeth in the table 28.33. So but here we need to calculate the Y value for 26.87 teeth. So that means you don't think that 26 practically there is no fraction of teeth. I can round it up to 27 or 26. Then based on that I need to calculate the Lewis form factor. Don't do that. That is not the correct way. So because here these are not the actual number of teeth. These are the virtual number of teeth. So virtual thing you can have any number because it is an imaginary thing. So you cannot round it off or modify that. You have to take as is. So therefore you have to calculate the Lewis form factor for 26.87 only. So now if you refer the same, that is 28.33 table in your data book or the material shared by me. So for 26 teeth it is 0.344 and for 28 teeth it is 0.352. Now using those two values you need to interpolate for 26.87. So now this is the formula of interpolation. So if I interpolate between those two values, I'll get Y as 0.3475. So this is 0.352 is for 28 teeth, 0.344 is for 26 teeth. So if I use the interpolation formula, I'll get Y is this much. Then the beam strength formula is SB is nothing but Mn into B into sigma B into Y. You know everything. Mn is given, B is given, sigma is given. Y is just calculated now, so you need to substitute that into this formula so that you'll get the beam strength. So Mn is given 4 mm, B is face width 40 mm, SUD is given as 600. So SUD by factor of 53, will get sigma B. Then Y is 0.3475. If you substitute and calculate this, you will get 11,120 newtons. The beam strength is 1120, 11,120 newtons. Similarly, you can calculate the wear strength also. So why we are calculating on beam strength and wear strength? So we need to check which one is the lowest one. Based on that only you can calculate the rated power. So coming to the wear strength, so this is the formula for Q. 2Zg by Zg plus Zp. So like I said, either you can use virtual number of teeth or actual number of teeth. So the formula, the value of P is going to be same. It is not going to change. It comes out as 1.667. Then your dp dash, if you want to use dp dash in the formula, you can take it as Zp into Mn by cos phi. So if you substitute that, number of teeth on the pinion is given as 20, normal module is 4 mm, cos 25 degrees, so which comes out as 88.27. Again, don't round off this one because it is a virtual pitch circle diameter, not the practical pitch diameter. Don't round it off this value. You have to take as these only. So whenever you have a virtual numbers, don't round it off those numbers. You take it as these. So now in that this is the equation for sigma E, what he has given in your data book. Sigma, oh, you got sigma E, all these things here in this. Maybe there is something wrong. Okay, so I think a BHN is given. So in that BHN, okay, if I want to calculate, okay, so we need to calculate PT. Okay, right. So this is what he has given, sigma data book. Sigma E is equal to 2.8 into BHN minus 70. So which comes out as 770 of Newton per mm square. Then using sigma E, we can calculate K or KW. So K is, formula for K is sigma E square sin alpha n divided by 1.4 into 1 by E1 plus 1 by E2. If I substitute just now sigma E we calculated, which is 770, alpha n is 20 degrees, and E1 and E2, both are made of same material. So I'll take same X modulus value for both gear as well as pinion, which are made of steel. I can take it as 2.07 into 10 power 5 Newton per mm square. So if I substitute that and calculate, the K value comes out as 1.399. So once you have K, then you know everything in the formula for SW. So you can calculate the wear strength. So wear strength SW is nothing but BQ dP K divided by cos square psi. Here mistake, it is dP dash. So then you'll get this one as 40 into 1.667, 88.27. 1.399 divided by cos square 25 degrees. If you substitute that, we get it as 10,027.783 newtons. So if you compare this SW to SB, your SW is less than SB. So beam strength is around 11,000. Here it is around 10,000 only. If I go here, 11,120 beam strength, and wear strength is only 10,027. So wear strength is the minimum value. So therefore, the gear tooth are going to fail by fitting failure. So therefore, your SW is going to be the failure criteria, or this is the load you have to use to calculate the power transmitted or rated power of the gear tooth. So since wear strength is lower than the beam strength, fitting is the criteria for the failure. So then from this fitting wear strength, we will calculate what is the tangential force, that is PT. Then once you have PD, you can calculate MT and you can calculate the power transmitted also. So this is the formula for V, which is 3.327 meters per second. And CV, okay, I have taken like what he has given in the data book. I use the same formula, 5.6 plus root 2V by 5.6, so that you will practice like this, so that it is familiar here. See now, I got CV is more than 1. So far in all our previous problems, we are taken in a reverse manner. The value of CV is less than 1. So in calculating the effective load, you need to take in a in fact, you don't require this one CV also, because You are taking the weight strength as the criteria. Oh, of course, I want to calculate effective load. Okay, for calculating the effective load, I require CV, right? Okay, so CV comes out as 1.325. Then your SW should be equal to P effective into factor of safety. So your P effective is nothing but CS into CV into PT into FS. See here the difference. So far we are written CS into PT by CV. This is the formula what we use so far. But here, since I reverse this formula for CV, here also the CV will also come into the numerator, not in the denominator. So now SW is known to us, it is 10,027.783. CS is given as in the problem data itself, is given as 1.5. CV we calculated as 1.325 and PT is unknown for us, we need to calculate that, and factor of safety is given as 2. So then from this equation you can get the tangential force PT. Once you have PT, then you can calculate the torque transmitted. If you simplify this equation, you will get the tangential force or tangential component of the force is PT as 22,521.28 newtons. So once I have PT, then I can calculate the torque, which is I have a relation between torque and PT, which is nothing but dP by 2 or dP dash by 2. To be precise, it is dP dash 25.21.28 into 88.27 divided by 2, which comes out as 1,11,276.96 Newton mm. So once I have MT, I can calculate the rated power. The formula for that one is this one, 2 by NP into MD by 60 into 10 power 6. If I substitute the respective data, I'll get the rated power in kilowatts. So it is going to be 8.39 kilowatts. So like this, you need to solve the problem. So similar lines and similar problems, same way you need to solve it. But only thing is, same formulas like what you use in case of spur gear. But only thing is, you need to take the equivalent parameters of your virtual spur gear. So in that, first step is we calculated the virtual number of teeth. That is number of teeth on that virtual spur gear, which is given by ZT by cos cube pi. So you got it is there. Based on this virtual number of teeth only, you need to calculate your Lewis form factor. Once you calculated the Lewis form factor, of course, this data is available from the tables only. Based on the pressure angle and number of teeth, you can calculate it. Because always in case of helical gear, you will get a fraction number of teeth. You need to use the interpolation to calculate y. Then once I have y value, so I know everything, so I can calculate the beam strength. So once I calculate the beam strength, then I will calculate the weight strength also, and I will compare beam strength and weight strength. Whichever is going to be the lowest one, that is going to be the criteria for the failure. So in this case, we got the weight strength is the minimum lower value when compared to the beam strength. Therefore, weight strength is the criteria. Of course, to calculate that weight strength, you required Q, you required K. So this is the formula for Q, and for K, this is dP dash. In that formula, you are going to use that one, and K is calculated from the again formula given in the data book. You need to use these two formulas to calculate K. Then you will get, this is the equation for your SW. Even this equation is also there in your data book. No need to remember all these things. If you substitute, you will get weight strength. Now clearly you can see that weight strength is less than the beam strength. Then weight strength is the criteria for the failure. Then based on this weight strength, we will try to calculate what is the rated power of the gateway. So for that we require V. Once you know V and CV, you can calculate the tangential component of a force on the gear. Then using this PT value, we can calculate the torque transmitted as well as the rated power. So like this, you can solve the problem. Okay, so this is one problem, and we'll try to take up one more problem. So this is the second problem what we are going to discuss in this helical gears. So I think with this we covered everything in helical gears also. So this problem we'll discuss in the next class. But time being, still you have 5 more 10 minutes time is there. Just you note it down this problem, and we will discuss its solution in the coming class, maybe tomorrow. Okay, note down this problem and respond to the attendance sheet, and you can leave the class. So, or else if you have any doubt in the previous problem or previous in this today's discussion, you can ask your doubt also.